I myself do not work in nuclear physics, so I learned a lot of nuclear physics during this week here, but I enjoy very much because how ideas also from nuclear physics enter in different fields. So I will talk more about electronic structure calculation here actually, and mainly about the problem of electrons in a magnetic field. So
bottom down.
Bottom down. Okay. So my motivation is the old effect, and I'm sure this story could also happen in Professor Keller's office, also a young graduate student, Edwin Hall, who came to his advisor, Professor Rowland, and he records this story actually in his publication. So this is the publication of the Hall effect, where he writes, starts with, sometime in the last university year, I was reading Maxwell's Electricity and Magnetism. And Maxwell writes there should be no permanent effect due to magnetism on electric currents. And all was intrigued by this statement. He said, I brought the question to Professor Rowland. He told me he doubted the truth of Maxwell's statement. That's quite something. I now began to give the matter more attention and went to the lab hall, and a couple of months later he had an experimental demonstration of what became the Hall effect. So it was not anticipated by Maxwell. And I can give you only a glimpse here in this talk why maybe after all this Hall effect, which is now a standard effect, is in fact not that trivial, even on the simple classical level, because this is very core quantum mechanics, of course. So up to date there exists a perfect phenomenological theory of the Hall effect, but if you want to go to a microscopic picture, actually for the classical Hall effect, things become very difficult. And to show you why, let me give you this simple textbook explanation here, which is given on most Condensed Matter course books on the first couple of pages. We introduce a Hall effect. So first let me explain the basic setup. Here you have a rectangular plate, and there's a magnetic field perpendicular to this plate here. On the left-hand side, this conducting plate is held from a certain potential. On the right-hand side, a different potential, and therefore electrons are moving into the device. Now the explanation goes, and most of the time in the chapter of Sommerfeld theory of the non-interacting electron gas, initially electrons get deflected, a charge builds up at the surface, which generates a uniform electric field to exactly counterbalance the magnetic Lorentz force. So the idea is that some electrons, they end up here at this lower edge. Here's the depletion up here. Electric field is developing in the transverse direction. This is the Hall field, of course. And then this should be the explanation of the Hall effect. Now, the problem with this looks very reasonable, but if you think about the electrostatics of this proposal, you would have up here sort of line charge, because remember, this is basically a two-dimensional plane. And down here you have a negative line charge. And when you calculate the potential of a line charge, actually there's a divergence at this line charge, and the potential between two line charges is by no means uniform linear potential. It's only between two infinite parallel planes, of course, this gives you perfect potential, but this doesn't work if the system is actually the plane. So the problem is actually where are the charges standing, or how is this field generated? I should point out these colors here are not printed by me, but this is a picture from experiment done in the group by von Klitzing. Actually, this is on the integer quantum Hall effect, but it gets a similar potential. And this color here indicates the color scale that the potential is in fact experimentally verified to be more or less uniform across the device. Things get a little bit even more strange when you consider the inverse problem. Now you want to generate a uniform potential. What type of charge distribution is doing this? And you find that there is no finite charge distribution which can do this. So how can this be measured? And at the same time, on the theory, you are running into problems. So I hope in the spirit of also of all the interest of people here, that's a rather simple problem. The question is, does it have a simple, clear-cut answer? And I can only partially point you in the direction. Now, what I want to do in the talk is now switch away a little bit from the classical Hall effect and move towards more quantum mechanical effects concerning these electrons in magnetic fields. And I want to reduce, of course, the model also to fewer electrons, to go away first from this big transport problem, and I want to move towards smaller systems. And I will give a very brief review of electronic structure methods, and I want to emphasize what I found interesting is that there is now a common search for method development, where also many things from nuclear physics are entering in quantum matter calculation. Now, the basic problem is that, of course, in electronic structure calculation, the Hamiltonian is well known, so the forces are there, there's no problem with that. But the diagonalization of a many-body problem is still difficult. So that's always the case. So the maximum you can do are 7 or 8 electrons. So that's not a lot. You can only solve directly by diagonalization in small systems. Then there's a big development of density functional theory, of course, which is very nice to reduce a many-body problem to just a single effective single particle density, where you integrate out all these complicated wave function parts. There's a huge reduction, and there's also a huge price you have to pay. Namely that you are basically limited to ground state properties, that the exact functional which achieves this is actually not known, and that in the end you are losing access to very interesting information, for example, to pair distribution functions and to the internal structure of the system, which would be very interesting, as I will show you. Then there's the more drastic reduction in the spirit of the values of the classical Hall effect. We'll think of n particle described by trajectories on purely classical level, and the state vector of the many-body problem is just given by position and momentum. And then there are sort of hybrid methods, or in between. You can consider pure state dynamics, where you enhance the classical state vector by additional degrees of freedom, like the width of wave packets and variation parameters of many-body quantum wave functions. That's the direction I want to go here in this talk. So I want to discuss this interplay between classical methods and quantum mechanical methods in the following. And since I'm talking about the Hall effect, I want to show you such a mapping which was achieved between classical and quantum mechanical states by Laughlin, who got the Nobel Prize for this in the context of the fractional Hall effect. What he pointed out, probably many of you are familiar with this, nevertheless I will give you a very short repetition, that it's possible to map the quantum mechanical state of this, what is now known as the Laughlin wave function, into a classical system. And the idea is the following. He proposed to write wave functions of the interacting electron systems in terms of this polynomial, where again, the electrons are confined to the planes, these are the coordinates of the electrons, and by constructing this polynomial, you make sure that, of course, no two electrons can be at the same place. Because here you have a difference which goes to 0 in this polynomial for the wave function ansatz. The probability density is then just this wave function squared. So you get here absolute value squared of the distances, and this restores the normalization of the wave function. And then Laughlin proceeds and said, well, this is an object which requires some interpretation and for practical calculation, and I can interpret this as a partition function of classical statistical mechanics. And this can be done in the following way. The norm of the wave function is a constant. So this is your one here, this is the left-hand side, this is the constant of this equation. But I can divide the right-hand side, I can leave this part here as an exponential of the inverse temperature times the classical potential. And the classical potential, when you want to reproduce this term, is in terms of logarithmic interaction between the electrons and a positive interaction, so harmonic velocity interaction with the background.